See this single line of code? Looks pretty simple, doesn't it? But what if I told you that its journey from your screen to actual execution is this incredible high-speed adventure that happens billions of times a second right inside the heart of your computer? Well, today, we're going to follow it. So yeah, have you ever written some code, hit run, and just moved on? What is actually going on in that split second? We're about to peel back the layers and follow one single command as it travels through this amazing miniature world that exists inside this. The CPU, the central processing unit. It's the undisputed brain of your computer. It's really just a spectacular piece of engineering that grabs your command, figures out what you want, does all the work, and makes everything happen. And it does this billions of times a second. It is the engine that powers our entire digital world.
All right, so to really understand this whole journey, we first have to meet the key players inside the CPU. And of course, we need to introduce the hero of our story, one single, very simple instruction.
You know, the best way to wrap your head around the CPU is to picture it as a master chef running a super high-tech kitchen. This analogy is going to be our guide through this whole process because everything inside that CPU has a role that perfectly mirrors a busy professional kitchen. So let's meet the kitchen crew. First up, you've got the control unit. Think of this as the head chef, the one who reads the recipe and tells everyone what to do. Then there's the ALU, the arithmetic logic unit. That's the stove. It does all the actual cooking, all the calculations. And the registers? Well, that's your super fast kitchen counter, holding only the ingredients you need right this second. And here it is, our protagonist, an instruction. It's really just two parts, an opcode, which tells the CPU what to do, and the operands, which tell it what to do it with. Our hero for today is add R1, R2. All this means is, take the number in register R2 and add it to the number in register R1. Sounds simple enough, right? Let's find out. Okay, our instructions journey is officially starting. First things first, the chef, our CPU, needs to get the next step of the recipe. And that recipe is stored in the computer's memory, in the cookbook. This whole process is called the fetch cycle. Every single instruction, including our little add command, goes through this exact same four-stage loop. Fetch, decode, execute, and write back. The CPU just does this over and over and over again, like a heartbeat. This is the fundamental rhythm of all computing. Check this out. This shows the entire cycle right in action. So before we start, a special little register called the program counter, or PC, is pointing to where our instruction lives in memory. Register R1 is holding the number 10, and R2 is holding 5. The CPU fetches and executes the command, and boom, afterwards R1 now holds the result, 15, and the PC has already moved on, ready for whatever's next. But wait, how does that instruction actually get from memory to the CPU? It travels on something called the system bus. The best way to think of this is like a city's road system. You've got the address bus, which is like the GPS. It says where to go. You have the data bus. That's the truck actually carrying the goods. And the control bus? Well, those are the traffic lights, making sure everything happens exactly when it's supposed to. So once our instruction makes it inside the CPU, two key components take over. You've got the one that plans the work and the one that actually does the work. Let's meet the conductor and the calculator. Now, that control unit, the head chef, actually comes in two different flavors. A hardwired unit is like a custom-built machine. It's incredibly fast, but totally inflexible. Think of specialized chips. On the other hand, a microprogrammed unit is more like running software. It's a bit slower, but you can update it. This is a really crucial design choice in CPU architecture. Do you want pure raw speed, or do you want adaptability? Here's another way to think about it that really makes it click. A hardwired unit is like a music box. It plays its tune perfectly, instantly, every single time, but you can never, ever change that tune. A microprogrammed unit is like a DVD player. Yeah, it's a little slower because it has to read the disc first, but you can pop in a new movie anytime you want. So our instruction, add R1, R2, it knows it needs the data that's in R1 and R2. But how does an instruction find its data in general? This is where we get into the crucial art of what's called addressing modes. Honestly, this might be the best analogy for this entire concept. An addressing mode is simply how you tell the CPU to find the data it needs. It's just like giving delivery instructions for a pizza. So the whole point is how you specify that location. Immediate mode means the data is literally baked into the instruction itself. Direct mode gives a very specific memory address. And our hero, ADR1R2, it uses register mode. The data is already right there in the CPU's hands, on the countertop, and that's exactly why it's so incredibly fast. Now, this table shows you the real-world impact of these different modes. Get this, the exact same instruction with the number 400 in it can end up pointing to 3 completely different locations in memory. It could mean address 400, or address 701, or even address 200. The how you ask for the data is just as important as the what.
So far, we've followed just a single instruction. But how do we build processors that can handle not just 8 bits of data, but 32 or 64? Let's zoom out for a second and see how these simple ideas get scaled up. See, back in the day, you couldn't just fit a whole 32-bit processor onto a single chip. It was too complex. So the solution was absolutely brilliant. It was called bit slicing. And the analogy is perfect. If you need a giant 32-meter ruler, but all you have are these little 4-meter rulers, what do? You just line up 8 of them. Processors were built in the exact same way.
And this is exactly how it works. You take 8 identical 4-bit processor chips, these slices, and you line them all up. They all work at the exact same time on their little piece of the data. But the crucial link, the thing that makes it all work together, is the carry signal. It lets them cooperate on big numbers, just like when you carry the one when you're doing addition by hand.
So there you have it. We've seen the entire journey of one single instruction: fetch, decode, execute. It's a simple, repeatable loop. You could even call it the atom of all computation. But what happens when you take that simple loop and you repeat it billions of times every single second? Well, you get everything. You get your smartphone, you get video games, you get self-driving cars. That is the incredible power of the CPU's journey.